Hi everyone, we are researchers from Universidade Federal do Ceará, and we are here to share a little of our experience with parametric modeling. In this case specifically, with its application as a tool to implement green infrastructure in the urban field. The first thing we had to do was to understand the relevance of water as a major element in cities formation. Despite its relevance, the urbanization process was detrimental to environmental systems, especially to the water-related ones, making the citizens more vulnerable to natural hazards and the consequences of climate change. The current increase in flooding risks in cities has shown the need of a paradigm shift in how we treat our natural systems. Ecosystem-based adaptation emerges as a people-centric strategy to help them adapt for the events of climate change. It consists of a network of natural and semi-natural areas known as green infrastructure that, when combined with traditional infrastructure, also called gray infrastructure, deliver ecosystem services. Its effectiveness, however, depends on integrating solutions. Now, we are facing the challenge of finding the best places to apply green infrastructure, which also must address and incorporate solutions for the additional challenge of social, economic, and political issues. The advance in technology provided us with new tools to interpret the environment through computational modeling. Here, we seek to develop a parametric algorithm that interrelates different urban aspects to help the process of decision making and use a more strategic approach to employ green infrastructure in the urban environment. So we had to decide how to tackle the people's vulnerabilities in the urban context. Our approach was based on a multi-criteria analysis that considered local characteristics and the green infrastructure conditions as parameters for the algorithm. For this study, bioretention cells were the selected green infrastructure solution. This was mainly because they can be adapted in small areas and help to manage the volume and quality of the urban runoff.
So we first compose and structure a computational logic, try to interrelate measurable urban parameters. At first we define what will be those inputs, what will be the necessary data to identify the best locations for green infrastructure based on their efficiency. So we choose to use georeference data that was collected from a city's database, and this type of data is really interesting because they can relate geometry and tabular information, so allow us to design a great range of studies and manipulations. The shapefiles that we used were topography, roads, lots, building, and blocks. The algorithm was constructed using three phases: the initial analysis, the data processing, and the multi-criteria analysis. In the end, the algorithm constructs a map that identifies the most efficient places to implement the green infrastructure. In the first phase, we used the topography data and we made two initial analyses. So we made a water flow analysis, and this helped us to understand its burn-off behavior in the area, trying to identify where is greater and where the water potentially accumulates. Then we did a hypersometric analysis to map the higher and the low levels heights of the land. So the second phase was crossing data. We add the road information to the results that we found on the first phase. We determined the number of intersections between every water runoff line and the road lines. We tried to create a retention potential criteria through the identification of the water flow behavior, and then we made an average intersection index. There was a mathematical evaluation because the roads have different dimensions, so we calculate the number of total runoff intersections divided by the extension of the respective road. As the first and the second analysis, we cross hypersometric and the roads. We make this using the geometric projection. So we pointed and mapping the average level heights of each road, and we classify them in orange areas, middle areas, and bottom areas. The classification was using the height level across the road, and for this criterion we consider the roads on middle level heights, that should be the yellow colors, would be most appropriate locations for setting of green infrastructure. And this happened because the middle areas, they receive water from the top areas, and they have the potential of function like interruption to the natural water runoff, so it helps to prevent flooding in the bottom areas. Then, to make a multi-criteria analysis, we create the third parameter that was based on the road hierarchy, the size of the road. We determined the score for each road hierarchy, giving values to the height scores to the ones who have more capacity of receiving bioretention cells. With these three criteria that we establish, we developed a variable score system to find and search for different scenarios. The criteria function works as a variable that can be modified and manipulated in different ways. The result map is a demarcation of the roads that got the best score, and then the demarcation works with a gradation of colors for the visual identification of green infrastructure execution potential. The red is for the roads who have the higher potential, the yellow for the roads who are in the middle, and the blue are for the roads who have low potential. As a result, we get a map using a visual approach, and this map is a variable he can change according to the inputs, according to the criteria that we use. So this will allow us, the reader, a better understanding of the area, and somehow the focus that we have is give enough information to make a more oriented decision. Results shows the same road with different classifications through his extensions, and we have different performances when we change the context or the inputs. Our analysis explored the use of an algorithm to determine the best places for implement green infrastructure. So we use this like a tool to find a better visualization of the urban complexity, and this kind of visualization creates a new way of intervention. We can anticipate and look for the sites looking for the better potential, but instead we get a range of alternatives. This is important to make a more informed urban interventions for the future. However, our inputs were limited, considering just aspects of the urban morphology, and this maybe will be problematic from a socio-economic perspective. The lack of this information will not be good for the local citizens, and the benefits of the potential cultural impact of this intervention, there is something that we cannot measure to incorporate in our algorithm. Our research represents a step further for development of a tool that will help in decision making by the use of physical, behavioral, and geometric inputs. However, there is a complex context of social and cultural needs that influences the choice of these decisions, and there are other variables that are subjective to the urban planner's perception that wasn't considered for this study, but must always be taken into consideration in the planning process. The great advantage of working with a parametric approach is that its structure is the same, so with the change in input data generating a dynamic and interactive scenario analysis. Thus, this can be used for a tool for adaptive planning. For the near future, the present work seeks to incorporate more cities variables. So thank you, we are really grateful to be here, and we want to say a special thanks to the Universidade Federal do Ceará. Thank you.